The elements of the periodic table.
There's hydrogen and helium, then lithium, beryllium, boron, carbon everywhere, nitrogen all through the air, with oxygen so you can breathe, and fluorine for your pretty teeth, neon to light up the signs, sodium for salty times,
magnesium,
aluminium, silicon,
phosphorus,
then sulfur, chlorine, then argon,
potassium,
and calcium so you'll grow strong,
scandium,
titanium, vanadium, and chromium, and manganese.
Hi, I'm here with Tony DeAngelis, and today's show we're going to be talking about elements. And Tony, thanks very much for being with us today.
Well, thanks for having me. I appreciate it very much. And as you know, elements are one of my passion. I really enjoy talking about them, and hopefully, you know, we can have some fun with it.
Okay, that's great. And from what I've seen up to this point, I think we're going to have a lot of fun with this. So, Tony, let me first ask you, what is an element?
Okay, an element is a substance which it is a basic part of the universe. Basically, it can't be subdivided into further things. If you have a compound like water, it's H2O, okay? 2 hydrogen, 1 oxygen. They can be divided, but the oxygen cannot be further divided. It can be split into its component parts, but it is a unit. There's no further subdivisions of it, so it's considered a basic part of matter.
Okay, so everything around us is made of elements.
Everything, including us.
Including us. Okay.
They come together as compounds. Generally, you don't find a pure element, but you'll find, you know, they'll be in combination, in compounds. They say 70% of the body is water. Well, that's the hydrogen and oxygen. So those are 2 elements. They say we're carbon-based, so you have the carbon as it. We have nitrogen that's very important to life. So there's many things, and they're all part of us.
Okay. So, for instance, we have a certain percentage of elements that make us. The Earth's surface would have a certain percentage of different elements that make up the Earth, and there's probably a different percentage of elements that make up the crust of the Earth, the mantle of the Earth, and the core of the Earth.
Correct. Right.
Okay. And similarly, the ocean would have its own composition.
Oh,
of elements.
definitely. Yeah. Now, as far as the core of the Earth, they think is mostly nickel and iron.
Okay.
And it's supposedly, they think it's also spinning, and that's what generates the magnetic field. But again, this is postulated from the evidence, but there's no physical way to determine this.
Yeah. Okay. And those are heavier elements, and they would have tended to, under the force of gravity, go to the center of the Earth, and that would be how they got there. Okay. Some of the basis for understanding elements takes us back a little bit to what's the structure of the atom.
Exactly.
So I think we need to mention that a little bit. And we all have this picture of, at least you and I, based on our age, that the atom was sort of like the solar system.
Right. You had the nucleus and then the planets revolving around it. And now it's quite different, but you can explain that.
Right. So the nucleus is comprised of the protons and the neutrons.
That's correct.
Okay. And then around that is the electrons.
Right. Now, for a stable atom, the number of electrons equals the number of protons.
Okay. Okay. And the number of protons is the atomic number.
That's correct.
And that's going to be important as we go on a little further. Okay, so that model of the atom is called the Bohr model.
Yes,
B-O-H-R,
right.
Niels Bohr.
That's correct. He developed that originally.
Okay. A Nobel Prize winner.
That's right.
Okay, so he did have his act together.
Yes,
Okay.
he really was good.
But now the thinking is that electrons really don't function like planets revolving around the sun, but rather they're more in a electron field,
Yes.
electron cloud, that they can be in
Right,
any
right.
place.
Yeah, because they don't have a particular defined orbit. They're just in there, right.
Okay, okay. So the elements, how are they organized, and how does man convey that organization of the elements to one another?
Well, basically today we have what's called the periodic table, which you see in front of you. And most of this was done by Dmitry Mendeleev. And when he started, he wanted to categorize some of the elements or figure out a way to do it. Now, the alchemists had, even though they were trying to find a way to make gold from base metals, they actually were the forerunners of the chemists. And they discovered a lot of the elements. And, excuse me, what he did is he came around and took all the known data and put them on index cards. And he had hundreds of them, and then he started to coalesce them. And he decided to try to put them into some sort of semblance of order. And what he wanted to do was to make them you have both columns and rows. And it was to, they had similar, like this first row here is called the alkali metals.
First column.
I mean the first column, excuse me. Alkali metals, and they're very, very reactive. And the reactivity of those is also shown here with the halogens. And in one group they have to, they want to release electrons, and in the other they want to acquire electrons. But either way, they are highly reactive, and anything with those properties he put together. And then he did, you know, like things with the rows and the higher atomic numbers, where they had more protons in the atoms. And he eventually decided to make the table. And when he did it, it was primitive, but it was similar to this. And he was an extremely brilliant scientist. He actually took spots that were not filled with elements and left them blank, because he said, well, there should be one here. I don't know what it is, but the properties should be like this. He even figured some of them, and the weight should be this, and there's nothing there. And he left those blank spots, and later on, as we discovered more elements, they were filled in. I think the latest one natural element to be discovered might be rhenium, number 75, but you know, these spots were left when he didn't have something to put in. So he was incredibly brilliant, and he left these blank spaces, and everything else was sort of put into a table. Now, in the last column there, you'll see what's called the noble gases: helium, neon, argon, krypton, xenon. And they almost interact with nothing, okay? That's why they call them the noble gases. And, you know, he put those in because they had similar properties in that they were non-reactive. And then the halogens being very reactive. So
Those are this column here.
yeah, that column there.
Let me ask you this about the noble gases. Helium is in that column. Is that
Right.
considered a noble gas?
It is, because it's not very reactive, okay? If you wanted to get technical, it probably shouldn't be, because it's not as inert as the others, but it still doesn't have a highly reactive capability.
I see.
So that's where most of those came from, and he did work for many, many years, and other scientists later contributed, but Mendeleev is considered the father of the periodic table.
And clearly he was respected by his peers.
Oh yeah, it
since
wasn't.
they actually named
Yes,
an element for him.
That's correct.
Atomic number 101.
yep, highly respected.
One thing that we didn't mention, and we probably should, about the atom, and that is the electrical charge, that the protons have a positive charge and the electrons have a negative charge.
That's correct, right.
And the neutrons have
No charge.
no charge. Okay, so that's a...
Yeah. Now, as I started to say before, with the alkali metals and the halogens, that's their reactivity is based on their electrical charge. In one sense, some of these elements want to grab electrons, and they combine with many of the other things. And these, they want to give electrons, and so they combine also or react very aggressively with different things.
So that that sharing an electron or grabbing an electron results in elements forming compounds.
Correct, right. So one of the simplest
like
ones.
H2O.
Or here's another one. You'll find this metal right here, sodium, okay, and this gas here, chlorine. And when they combine, you have this wonderful stuff that you put on your French fries, salt,
Right, but...
NaCl.
Right, NaCl, but Na by itself,
Is
and
deadly.
you mix it with water.
Yeah, oh
boom.
yeah, that's because of its reactivity.
Cl by itself.
It's a poisonous gas used in World War I.
And you put them together,
And
you get salt.
that's right. So,
Amazing.
yep, the combinations are virtually endless. You know, those are simple ones, compounds, but there are, you know, myriads of them.
Well, there's a number of properties that all these elements have. Why don't you show us a few?
Well, the first thing is most of the stuff from like this part of the periodic table, some of these aluminum, gallium, and indium, and all of these are all metals. Okay, metals, you know what a metal is, and metals are defined by properties of usually generally high density, they're well organized atomically, and so on. Then there are metalloids that you'll see here, and those are the ones that are, sometimes you have semiconductors, silicone, and you know, tellurium, and some of those things that sort of can go either way. A lot of them are used in the electronics industry.
So electrical conductivity would be an attribute.
Right.
Okay. Density.
Density is another
Density
thing.
would
Yep.
be an attribute.
Yep. And the metals have, you know, various densities. I mean, you can take one that's beryllium, which is extremely lightweight. I'll show you a sample later and weigh it for you. And then you have something like gold or platinum, which is extremely dense and heavy.
Can you show us some examples of density?
Sure, I can do it with these pieces of metal right here. If you want to see it.
Hand one to me.
Okay, do you want the scale?
You can leave that
Oh,
right
okay.
there. So this is
That is magnesium,
magnesium.
which is over here.
Okay, so here we are, magnesium. And this is fairly light.
Right.
This is fairly light. Put it on the scale,
Okay.
and we probably get a reading of
Maybe
a quarter of a pound, thereabouts.
Uh-huh.
Okay. Okay.
Now we have one a little bit heavier. This is molybdenum.
Molybdenum.
Yeah.
Okay.
And that's right here.
Okay, so that's 42, so atomic
Right.
number of 42, meaning it has 42 protons
Exactly.
and 42 electrons. This is pretty heavy. This is heavier than a baseball for sure.
Yep, and heavier than iron. It's
Yeah.
usually added to iron to make tough tool steel.
Okay. And that's about a pound. That's about a pound. So we have,
Yeah, from a very lightweight to a middleweight
so
here.
the volume of these is the same.
Right.
The volume is the same, but the weight is, this is very light, this is very heavy.
Now we'll go
Okay.
to one step further, the real heavyweight in the group.
Excuse me. Oh, okay. This is really heavy.
Yes.
This is like this is like sledgehammer type heavy.
Actually, this is as heavy as gold, and that's presented a problem. But this is wolfram, W, which is right here, tungsten.
Tungsten. Why
Yep.
don't you throw that on the scale?
Okay.
And I think that's coming in at around 2 pounds. Around 2 pounds.
Thereabouts. And, you know, you can see the density, the difference. They're all identical in size, but the weight is vastly different.
Vastly different.
Now, one thing that's come up, and
Interesting.
I don't know if you've seen it in the news, recently, people have been buying gold ingots, okay? And some of the ones, I don't know if you can say the name of the country, but some of the ones from China, they have found that they're a bar of tungsten inside. And what they did is they coated them with gold, but rather than a thin plating, they put like a full millimeter around it. But you've got a 10-kilogram bar of gold, which, you know, is very, very expensive. And then you go and drill down a bit, and you get through the gold, and you find the middle is all tungsten. Very upset.
Yeah, yeah. So normally when they assay a piece of gold, they'd scratch a little bit.
Right, and test
Okay.
it with nitric acid and
Okay,
such.
but in this case, you almost have to melt the whole thing.
Yes, or drill through it.
Drill
and
through
and the thing is, you know, you'll find a big slug of this inside because the weight is almost identical to that of gold.
Interesting.
Yep, so that's proven something for the criminal element to work with.
Okay, so we have connectivity, we have density. What are some other attributes?
Well, color is one thing too. You have some of the metals which are actually have a unique color to them: copper, silver, gold, and even osmium is one that has sort of a bluish tint. You know, generally some of them are used for ornamentation, as well and currency, as well as in industry. If you notice, most computers have gold contacts now.
Yes, very good
And
conductor.
it's the second best conductor. The best is actually silver, but silver oxidizes, combines with oxygen, and oxidizes so it loses something. So they use gold, which is completely inert and doesn't combine with anything. If you have gold from the time of the pharaohs, it's still gold. It's
I see.
unaltered,
It
even in
has-
seawater or whatever.
It hasn't combined with
No.
anything. Okay.
It's really unique.
What do you have here?
Okay, here is my pride and joy, which is an element collection. The periodic table here is by Theodore Gray. It's the same one as that, just smaller. Okay, and I had a friend make the holder here, and basically what I have is a collection showing many of the elements, and most of them, the ones that I could get, are made as a half-inch diameter, 1-inch long rod, and this is beryllium.
So the machining of these pieces is it's unbelievable. I
Yeah.
mean, these are all the same size.
Right.
Beryllium I'm feeling to be very, very light.
And then gold, substantially heavier.
Gold substantially heavier. You notice the difference in the color of these.
Copper is sort of midweight in between.
Yeah, and there's copper to see the difference in weight. It's kind of midway, but there's an example of the difference in
Right.
color.
Yeah.
Beryllium, like we were talking about before, was mined heavily in New Hampshire.
Yes,
in
from,
southern.
they had, in the pegmatites of New Hampshire, they had a lot of beryl crystal.
Yeah.
And that's what beryllium comes from mostly.
Yeah, so you'll have to look for one of our
right.
future shows going to a barrel mine in southern New Hampshire.
Yeah, that's
But
real nice.
this was very valuable in the Manhattan Project.
Yes,
in
it
World
was.
War II.
And it's
being,
also, now it's used heavily in the space projects. I have seen online beryllium, either casing and also the guts of spacecraft gyroscopes. They need to be made of very hard and high temperature metals, but weight is a concern. So you're not going to use tungsten or any of those things. You want something, and this is one thing that can be used.
So it just dawned on me, this is gold.
Yes, it is. 2 ounces.
2 ounces, 2 ounces of gold. Okay, that's the most gold I've ever had in my hand. Do you have platinum?
Right here next to it.
And there's platinum. And in terms of weight, they seem similar, but the platinum seems a little heavier.
It is.
Yeah, for sure.
Now the 2 heaviest elements that you can find are here, iridium and osmium. Iridium also resists more chemical activity than any other element. Osmium, it has that slate blue tint. I don't know if it'll show on camera.
Beautiful. This is osmium right here.
And iridium, if it's polished, it has almost a slightly yellowish tint, but not very visible. It's not silvery. Silver is silvery.
So this has a little yellow tint to it. The osmium, I can definitely see the blue. It's very striking.
Now,
the machining of these just blows me away.
this one
All
here
the
is a
same.
kind of, this one's a little bit bigger to get the full amount because he couldn't get it machined properly. But this is rhodium.
Rhodium.
Rhodium is one of the most expensive metals, and it's used for contacts in certain high temperature switches, thermocouples, and like that. But one of the funny things about rhodium is one of its main uses is to plate lesser metals. Like you'll have silverware. You plate it, or silver jewelry, you plate it with rhodium to make so that it would not tarnish. Now that seems counterintuitive because rhodium, it's silver at say $30 an ounce and rhodium at $1,500 an ounce. Doesn't seem like it's a brilliant thing to do. But what happens with rhodium is you do electroplating, and rhodium, for whatever reason in its atomic structure, it is the most opaque metal. So you only need a few atoms of thickness to cover the stuff. So you're using extremely small amounts to coat.
So a little rhodium
goes a long way.
Goes a long way.
Right.
Interesting.
And amongst the metals also, we have several that are sort of special in that they're radioactive elements. And I'll show you some of those.
I'm very comforted sitting so close to those, Tony.
Well, it's not going to provide any danger here. If it was, I'd move away and I'd leave you close to it.
So what do we have here?
This is a handheld Geiger counter, and it's pretty sensitive. And one of the things it can be used for, obviously, is detecting the radioactivity. And certain ones here are radioactive. And we'll show them. Americium, which is used in smoke detectors.
Yes.
These were from an industrial smoke detector. And you can see that it's quite radioactive.
Really hot.
Yep. We have here natural uranium. This is not depleted, it's natural. So it has some U-235 in it. Not a big, tremendous amount, but again, quite hot.
So is this in the form of an ore?
No, this is metal. This is refined metal.
Oh, okay. I see this. This is refined.
Excuse me.
Refined.
Wow. Yeah.
Refined. This is 238
and 235.
And 235.
Yeah. Depleted uranium, most of the 235 has been removed. This is natural, so it does have a little bit, but not anything where you'd have to worry. This is a little rod of thorium, and that's also,
Pretty hot.
yeah. So many of these things, exhibit radiation, and
Now, the average person around their house, would they have things that are radioactive? I mean,
Sure.
it seems like everyone has a smoke detector.
well, yeah. So you have the americium from a smoke detector.
Okay.
You would have. Sometimes people buy this salt that's made with potassium, and a lot of times there's potassium-40 in there, which is radioactive. Not heavily, but slightly, and it's in there. Also, some people have Fiesta ware.
Oh, yes.
which is radioactive to an extent.
I think my brother owns all the Fiesta ware and...
Almost, I've got a piece. But here's something else. This is all radioactive. This is uranium glass, depression glass. And this greenish, color is indicative of the radioactivity and the uranium content in it. But under... Oh, got to plug it in. I keep forgetting that things work best when they're plugged in. But just to show you, this is something else that people may have around their house as a decorative item.
Whoa! Look at that.
And I'll shut the light for a moment so that you can see
Wow.
it in its glory.
Right.
So this is uranium glass.
Uranium glass.
And it has a slight amount of uranium oxide. It was molded into the glass to give it that beautiful green color in daylight and this marvelous glowy effect in, under shot a long wave. This is a long wave lamp.
For some reason, when I saw the glass, I didn't think you were into China.
No.
I thought it had some connection.
That's right. Yep, most of my stuff is...
Now, people that... There's a lot of people nowadays that buy granite countertops.
Yep, granite contains uranium and a little bit of radium, and because those things were found in the pegmatites,
Yes.
and uranium and stuff leaches through. That's why so many basements, especially in New Hampshire and Maine, have a lot of radon.
Yes.
Because of the ground having the, if you're on glacial moraine where it's all mixed until it doesn't matter, but if you're on the bedrock, you'll have a lot of those things seeping through and into basements. So they have radon detectors, and basically most of those are nothing more than chunks of activated charcoal. They absorb the radon and everything else. You send it to a lab, and they run the analysis of how much radon is there.
So the radon, I mean, uranium has this decay series.
Right.
Like uranium decays to
Yeah, radium, say, and right.
different elements.
Yep.
And radon is a product of that
Yes,
decay
it's
chain.
actually-
As I think thorium is too. I think
Yes.
thorium's in that.
Thorium is, I think, longer lived. Basically, the way the decay chains are also, radium is the exact precursor to radon, and
Yep.
we have done. I do have some stuff that we've done with that testing, and I think from radium to radon, for them to be in equilibrium where as much of the radon decays as is being produced
Yeah.
is 22 days.
22 days.
Yeah.
Okay.
That's to get it into equilibrium.
So that would be a half-life.
Basically.
Yeah.
See, and that's the other thing. The longer the half-life, the less worrisome the radiation actually is. Because if you have, say, something with uranium with a 1,000,000-year half-life, and you have radium with a 1,500-year half-life, well, this is putting out a lot more radiation because it's going through it quicker than say something with a long half-life. So you get francium, which is vanishingly fast, or some of these ones that have very short half-lives. They're putting out tremendous amount of radiation. So,
Yeah.
but to get back to the periodic table and give you some information, most mainstream scientists today don't consider any elements above 103. 103 is the cutoff. 104 to 118 are considered pseudo-elements in that they don't really exist in any form. Meitnerium, which was named after Lisa Meitner, they only found 10 they were able to make it in the reactor. They made 10 atoms. That's way too small to do anything with.
10 atoms.
And it only had a half-life of a few minutes. So you can't see the 10 atoms to discover anything about the physical properties because it's so little. And then in a few minutes, it's gone.
Yeah.
And some of these have I remember one 4/4,000th of a second life.
Yeah.
So you can't really do anything with them or discover anything about them. They usually just find the radioactive tracks and and that's about it.
Now, I notice here that there are several radioactive
Right.
notations here, and these spots are empty.
Yeah.
And some of that, I think, is attributed to them that there's not much of it available if you're saying there's 10 atoms.
Right.
But some are probably illegal to have.
Yes, like plutonium, you're not supposed to have any because it's a weapons, can be used for nuclear weapons. So plutonium is used for two other things. They make batteries with them. Some batteries are used in spacecraft that they send far away. No one's going to get it. The other one was used in some pacemakers. And they're so strict on plutonium that if you die with the pacemaker with a plutonium battery, it has to be removed from you before you're buried. That's how strict they are. So certain ones you would be put in prison if you owned. Others, they're not so crazy about. But, you know.
Tony, can you say a few words about how elements are created?
Okay, most elements, you have to go back to the Big Bang, and in the formation of the universe, you had primordial elements that were created. The first and most abundant was hydrogen, which is simply, you have one proton, one electron, and it's a very simple one. The next thing that was, I think it was, I forget the percentage, if it was like 78%, then most of the remaining one is helium, which was another big percentage of helium being created, another very simple atom. And then they postulate through a process called spallation that there were several other of the low-density elements, lithium, beryllium, boron, and possibly carbon and nitrogen, but those are, after that.
And when we say light, we're referring to they don't have a lot of protons.
Right.
And that speaks to the
Yes.
light.
And what happened then is, after that, most of the elements that we have today were formed with nucleosynthesis. That's in the cores of stars. Now, when you have hydrogen, if it all burns out and the star has enough fuel, it will start burning helium. Then it will go to lithium, beryllium, and so on, boron into carbon, and it will continue. And it will actually work its way all the way up the chain until it hits manganese. Once it goes from manganese to iron. Manganese will fuse, but iron will not. It takes more energy to fuse it than it releases. So at this point, fusion stops. Now, all the heavier elements in the periodic table are produced in supernova. When a star explodes, basically your physical laws are somewhat suspended. There are tremendous forces at work, and it will create all the heavier elements, all that we know.
Very interesting.
And finding them, what's been corralled together under the force of gravity and coalesced into the crust of the Earth, you'll find many of these elements. Some you'll find in their native state. Nickel and cobalt are sometimes found raw, but copper very often. Silver is found like that. Gold, of course. Some mercury. Platinum is found native, and osmiridium are found combined in their native state. But generally, most of the others, say uranium, tellurium, and all of them, they find as ore materials.
I see, and they have to be refined.
They have to be refined and taken down. So sometimes, that's why I say I admire the alchemists, because they would grind down this stuff and go through process after process, and a lot of them kept good records of how they came out with this final thing. And the guy's trying to find gold, and he finds zinc. Okay, well, this is no good, throws it aside. Well, today zinc, it's not a precious metal, but it's used to galvanize everything, so it was a discovery that was of merit. And,
Tony, how did you get interested in this?
Well, that's a kind of a funny story. My interest grew from a comic book. I was an avid comic book reader, and there was this book that came out in 1962. It was an issue of Showcase magazine, and Showcase magazine in 1962, with this group of unique people called the metal men.
Metal men.
And there was gold and iron and mercury and lead and platinum and tin that the scientists created. And in the book, they would have like little factoid pages. And the metal men here, they had factoids, you know, they talked about mercury being the only liquid metal, which is the only metal that's liquid at room temperature. And then they talked about gold and said how it could be drawn, an ounce could be drawn into a wire thinner than a human hair, 50 miles long. It's the most ductile and malleable of metals. And I got interested in that, and that just pursued into my my rock collecting, because then some of the rocks, of course, are metal ores. So then I read up more on that, and then I became more interested in metal elements as the pure elements. And my friend in Virginia was selling some small samples, and then I found, you know, online later this company where they made, you know, substantial ones. And as I said, I endeavored to get all I could, you know, so silver, copper, and stuff. Some of them, as you can see, these little, well, some of them are ampules of small amounts of elements, simply because they are rare earths and they have to be under argon or they would basically decay away.
I see.
In oxygen. The guy did online, he has a series of shots, like 1 day, 1 week, 1 month, 6 months, and a year. And some of the rare earth ones, which are especially these, cerium and lanthanum and paraceodymium and neodymium, samarium, europium, those will actually crumble away if left out in the open. These have a little bit of tarnish and patina, but they won't crumble. But these will, so I had to get the small samples in argon, and it's nice and shiny. And
In argon, which is
inert, right.
Inert.
So that's where most of the stuff is packaged under argon. It doesn't react with anything, and it keeps them safe and sound.
Well, Tony, this is fantastic. I'm
Thank you.
overly impressed, and I hope you're impressed too. Tony, I want to thank you very much.
Oh, thank you.
for,
It's a pleasure.
taking time to talk to us
Not at all.
about this, and I look to maybe in the future doing some more with this.
I hope
And,
so.
I hope you all enjoyed it, and we'll see you next time.
This is the periodic table, noble gas is stable, halogens and alkali react aggressively. Each period will see new outer shells will electrons are to the right.